Okay, but in the meantime, let's see where we are right now, right? So we figured out in general how to learn support vector machines. It's a quadratic programming problem, right? It's got, these inequality constraints, and it's got this quadratic objective, which is just the norm of the weight vector. We can just use an off-the-shelf quadratic programming solver for this, right? I mean, there's people in, applied math and operations research that do nothing but come up with better mathematical programming techniques, right? This is a very unfortunate overload of the term programming, right? Linear programming, quadratic programming, mathematical programming, they're really not programming in the modern sense, right? They're just optimization. But nevertheless, there's things like this that are just, available. Some of them open source, right? And indeed, this is what people first did, right? Is they formulated their learning problem, and then they threw this into a quadratic solver. The problem with that, as is usually the case in machine learning, is that just using the off-the-shelf optimization solution doesn't get you very far. In particular, think of doing a support vector machine with 1 million examples. This is doing a problem with 1 million constraints. Even for state-of-the-art, expensive commercial optimizers, this is going to be a really tough thing to deal with. Right? You might have to wait a long time. You might run out of memory, etc., etc. So the next step, as usual, is let's come up with our own optimization techniques that are geared to the problem that we're trying to solve. Okay? And then people have there's all these algorithms for learning support vector machines, which are in one way or another trying to solve this constraint optimization problem. Okay? Let me just mention what is probably the most famous one. It's something that you can get for free on the web. It's called sequential minimal optimization. It was actually invented by John Platt, who's a researcher at Microsoft Researcher, right? Or at least he was one of the people who initially developed this. So what is sequential minimal optimization? Right? It's actually in some ways much simpler than a lot of the quadratic programming techniques that it's beating. And as I said, this is not necessarily the best algorithm, but just to give you an example of how you might solve this problem in practice, here it is. There's some more scalable ones out there these days, and but for many problems, people still just use what's called SMO. Let's start from solving an unconstrained problem, right? There's something even simpler than gradient descent that sometimes works and is very easy to implement, which is called coordinate descent. Has anybody heard of coordinate descent? Coordinate descent is actually sometimes a good tool to have in your bag because it's so simple. It's just this. I'm going to optimize along one coordinate at a time. Right? I want to find my minimum of the function. Don't compute the gradient. Right? Let's suppose that computing the gradient is too hard for some reason in our case. Then what can I do? Well, one thing I can do is coordinate descent, which is that, well, I want to find the minimum along x and y. Well, let me first minimize according to x. And then I minimize along y. And then x and then y, and hopefully not too many steps, right? Of course, in many dimensions, I'm going to minimize along, d things in turn, but that's coordinate descent. Now, you can already see that in many cases, this is going to be ridiculously slow, right? But in some cases, it's okay. And it's very, very simple. Now, let's suppose that we wanted to use coordinate descent for, support vector machine optimization, right? There is a very big problem in this, which has to do with the fact that, in fact, gradient descent would suffer from the same problem, which is I can't just do that, right? Because I'm going to, jump out of my constrained surface, right? I can't just be doing coordinate descent, on one coordinate at a time along my, of my goal function, right? Because I have to keep the constraints in mind. What this means, right, is that I cannot update one alpha I at a time. Right? Coordinate descent is like improve one alpha at a time, meaning optimize the weight of one example, supposing that the weights of all the others are constant. Right? Let's suppose they're all 0, and I'm going to optimize this one to kind of put the hyperplane in the right place relative to it. And I'm just going to iterate through the examples doing this. Right? The problem, though, is that this does not work because it's going to violate my constraints. Right? I have to keep satisfying my constraints. So the SMO is really the answer to the following question. What is the least thing that I can do that is as close as possible to coordinate descent while making sure that I'm always satisfying my constraints? Okay? And it actually is the following. And again, I'm not going to show this, but hopefully it won't be too unintuitive, right? Here's the idea. I'm just going to do the following. I'm going to find an example that violates the KKT conditions. remember, we saw that this solution has to satisfy the KKT conditions, right? So if there's an example whose constraint is currently not being satisfied, meaning it's violating its margin constraint, well, I better do something with respect to that example, right? But that's not enough, right? That would be coordinate descent. The other thing that I have to do, and this is sort of like what's new and clever about SMO, is that I'm going to select a second example using some heuristics which I won't go into, but the whole idea here is that I can't optimize one example at a time while staying in this surface, but I can optimize two. Basically, I can change the weight of this example as long as I have some other example whose weight I change to compensate, such that the total value of this thing stays the same. Okay? Roughly speaking, that's the idea. And then what I do is I jointly optimize over alpha I and alpha j, meaning the weights of the two examples. So instead of, coordinate descent, this is descent along pairs of coordinates. And the thing is that, well, descent along pairs of coordinates is just solving a problem on the plane. It's no big deal, right? And what I'm going to do is basically iteratively solve these problems on planes until finally I converge to the optimum. I know that I've converged to the optimum when all my KKT conditions are satisfied. Okay? In particular, the complementarity conditions are satisfied, meaning that for each example, either its weight is 0 or it's on the margin, meaning its margin is 1. Okay? Questions? Okay, very good. I realize this was a lot of stuff. There's a couple more things to do that we will do next time. They have to do with handling noisy data, right? Here's the thing to leave you, in suspense for the next week, right? Is everything that we've done so far is actually pretty much useless as far as the real world goes, because we still haven't fixed the biggest problem that the perceptron had, which was it couldn't handle noise. Right? One bad example made it go crazy. We still don't know, despite all their beauty and power and max margin and kernels and whatnot, we still can't deal with noisy examples. So the first thing that we're going to see next time is how to deal with noisy examples. And the second one is actually what kinds of generalization guarantees we have on support vector machines coming from learning theory. Okay? And then we will look at dimensional reduction in clusters. Okay? And in the meantime, now you can do the rest of your project. So have fun.